وعليكم السلام دكتور.
Okay. So we'll start our lecture by an example as demanded by Abdullah, which highlight that the state space representation is ununique. So here I will start with example, and for that, let's assume I'm having a transfer function y over r, which will equal to 1 over s squared plus 3s plus 2. And simply, I need to describe this system, this transfer function, in terms of the first method, which we call the first canonical form or the direct method, and the second one, which is we call it the parallel method or the diagonal method, actually. So the first one, if you notice, simply of the system is what? Who can decide the order of the system? This transfer function, the order of this system is what? Simply the order of the system is the highest power of s. So the highest power of s is what here?
2.
2. So simply this means that I need how many state variables?
2.
2. So simply this means that x, which will equal to x1, x2. Yeah, because I'm having this vector and consists of what? Of 2 state variables. Now, if you notice last time, I told you that the direct method simply, if I need to use it directly, I would say that x dot will equal to 0, 1. Then here is the coefficient of the characteristic equation in the inverted sign. So this will be the -2, this will be the -3. And here this will be the x1, x2. Then I'm having only a single input, 0 and 1. And this will be the input, which is here r of t. Yeah. And y will equal the coefficient here, which is s to the power 0. So it will be x1. Yeah. Now I will redo it in detail, but simply let's do it if I'm understanding the first method and the second method. Now the second method states that I will get the roots of the characteristic equation. So simply if I'm solving the characteristic equation, and the characteristic equation is s squared plus 3s plus 2 equal to 0. If I need to find the roots, it will be s plus 1, s plus 2 equal to 0. So simply the roots are -1 and the -2. So this means that x will equal to, which is x dot, x1 dot, x2 dot will equal. Now, because here I'm having distinct roots, this means that this will be -1, this will be the -2, 0 and 0, and this will be the x plus. For the input here, I will have a direct input. I will have input in the first dynamic and in the second dynamic, r of t. Now, for y, I need to do the partial fraction expansion for that. And if I do the partial fraction expansion, it will be k1 over s plus 1 plus k2 over s plus 2. So simply this will be k1, k2 multiplied by the x. If I don't need to do anything, just only to highlight the, let's say, how to write or the form of the first method, which is the first canonical form or the series method, and the second one, which is the parallel method or the first diagonal method, or the, let's say, the parallel method or the diagonal form. Now, if you need me to go in detail how I get the first one and the second one, I will do it here for short. The first one, simply I state the first method. Simply you will say that first write y equal r over s squared plus 3s plus 2. Yeah, which means that simply this is the n of s over d of s, and I multiply it by the r. Yeah. Then I will take the r over d of s, and I will define it as x, my state variable. So here I will get y equal n of s multiplied by x of s. Yes or no? Yeah. Yes. And I will get x of s equal r over d of s. Correct? Yes. So simply for this example here, I will get y equal to x. And for this one, I will get what? I will get s square x plus 3sx plus 2x equal to r, which in time domain state that x double dot will equal r minus 3x dot plus 2x. Yes? I'm rearranging the equation. Find, let's say, the inverse Laplace transform, and simply rearrange the equation after that. Then I told you that ask yourself, the highest derivative here is what? Of order 2. So how many integrator I need? I need 2 integrators. Yeah. So this will be the x double dot, the first integrator, the second integrator, and here I'm having the x. So this will be the x dot. The output of each integrator is a state variable. So this will be the x1, this will be the x2. So y will equal to x1, yeah, because x is equal to what? To x1. And simply x2 is what? Is x1 dot, yeah, because this one is actually what? This actually is x1 dot, because if I integrate this one, what I'm getting? x1. So now what I'm getting something called cascading, which means that x1 dot equal to x2. Now x2 dot is equal my differential equation, yeah, because x2 dot is equal the x double dot, which will equal r minus 3x2. And this is a minus, I think, yeah, because I'm rearranging. Yeah, this is a minus. No one following me. So here this is a minus. Okay, so this will be minus 2x1, and the final equation I need is y equal to x1. Now, if I return back here, this will be the first state space representation. Now, for the second one, what I need to do, I need to do the partial fraction expansion, is to rewrite the transfer function into first order, let's say, factors. So this will be 1 over s square plus 3s plus 2. And if I do the partial fraction expansion, it will be k1 over s plus 1 plus k2 over s plus 2. Now let's see, Khalid Al-Jundi, k1 equal to what? Khalid. خالد الجندي مش موجود؟ طيب هاي ثاني مرة بنادي عليك يا خالد. يوسف البدر كمان يوسف مش موجود. طيب خير. مصطفى إياد. مصطفى. No one is there. Just a ghost. Okay. مصطفى. هيثم برهان.
دكتور زي زمان بنحط K1 يساوي S بلس 1 ضرب شو اسمه 1 على S تربيع زائد 3S زائد 2.
ايوه.
احنا بنكون محللينها اصلا او بنختصر هذا من اول.
So check. This will be what? 1, huh? S1, So this will be the 1 over s plus 1 plus k2 check minus
-1.
minus 1, yep, over s plus 1. Yeah. Then we say that I will write y equal r over s plus 1 minus r over s plus 1. Yeah. Yes. Now this one actually is the same as the previous one now. Why? Because I will take r over d as my state variable. Yeah. So here I will say that this one is x1, and let's assume this one is 2. Huh? What's happening today? 2. Yeah. And this one is what? Is my x2. So now automatically I'm having what? Y equal x1 minus x2. Someone will say, no, I will take the minus here. So this will be x1 plus x2. As minus. The state space representation is unique. It depends on how you are selecting the state variable. Yep.
دكتور
Yep.
بس هاي فوق بالمعادلة الكي 1 آخر شيء مش المفروض -1 over s plus 2
Which one? This one?
هاي الزرقاء آخر على اليمين.
Yeah. This one?
آخر إيش على اليمين آخر إيش على اليمين.
على اليمين. This one.
هاي مش المفروض -1 over s plus 2.
Yeah. That's why I'm not knowing why the one is stuck. All the time I'm saying 2, then I'm putting 1. Huh? Thank you. Yeah, this is the third time I think so. Yeah. Okay, okay, let's see. This is 1, this is 2. This is 1, this is 2. This is 1, this is 2. Okay, I get it now. Thank you. Okay. So now let's see. So simply this means that now I'm having the output equation, which is y equal to x1 minus x2. Then if I'm having here, this means that x1 dot will equal r minus x1. Yes or no? This equation. Yeah. Right here, x1 equal r over s plus 1. Then you will have s x1 plus x1 equal to r in time domain x1 dot plus x1 equal to r. Rearrange, you are getting what? x1 dot equal r minus x1. Who can help me with this one? This one's difficult because it has 2, man. It has 2. And I'm afraid that I forget. Yeah, this is difficult. It has 2. Who will help me with this one? x2 dot equal to what? محمد مجدي عبد الرحيم محمد مجدي نتي محمد سعد محمود نو اوكي طارق ايمن سعد
لا محمد محمود
محمد متى حكيت اسمك محمد انت؟
ما انا متاسف سمعت محمد محمود فمتاسف.
Okay, محمد محمود. Yeah. So can you help me with this one? x2 dot equal to what?
مش مفهوم. r
maybe this one is not hidden, so this is plus 2. See, x2 equal r over s plus 2. Can you simplify this equation? Can you find x2 as the time, let's say, the differential equation? Can you find the differential equation that represents this system? Yes or no, Mahmoud?
معلش مش مركز كثير صراحة.
Okay, what the first step? Do you know what this one is? This is a transfer function, huh? x2 over r equal 1 over x, yes? Now I need to find differential equation. So what I will do, I will multiply. So this will be s x2 plus 2, x2 equal to r. Yes or no?
Yes.
Is it difficult?
No.
No. S stand for what in time domain, Mahmoud? In time domain, any S stand for d by dt. Yes?
Yes.
So if you have two S's, you will stand for d2 by dt square, yeah? So this means that this is the first derivative, yes or no? The first derivative. And by the first derivative, we agree to use x dot. Huh? And do you see here any S?
No.
So this will be 2x. This will be the r. Now, if I need to write ordinal differential equation, I will rearrange this one state space in one side, and all the other terms should be moved to the other side. Let's yeah.
So r minus 2x.
Yeah, so this will be the x2 equal to r minus 2x. Thank you, Mahmoud. And this which x? Ah, do you see? I'm forgetting the two.
x2.
Yeah.
x2.
Yeah, thank you. I was searching for that, which x. So this will be the x2, yeah? Yeah. x2, x2, and x2. So now let's see. Yeah, this is minus 0, 1, 0 minus 2, and here I'm having k1, k2, and I think we agreed that this one is the 1, and this one is the minus 1, correct? Yeah. Now, the first question, the two representation here describing the same transfer function, yes or no? The two representation, ya Abdullah Isa Muhammad al-Khasani. Abdullah Isa. The representation in 1 and the representation in 2 describe the same transfer function?
100%.
Yes, so simply this means that the state space representation is ununique. What's the meaning of ununiqueness? Do you know the meaning of ununiqueness?
انه زي ما قلنا قبل شوي انه بيعتمد على شو نقول فرضيا، والله ممكن ناخذ ماينس مع الار، ممكن لا، فاختلف الموضوع.
Which means that it depends on your selection. Yeah, thank you. Your selection of the state variable. Yeah. Good. Okay. So why we are interested in the first representation and the second representation? Because the first one contains useful information, which is the characteristic equation coefficient. Yes or no? You see it? Minus 2, minus 3, 2 and 3, inverted in the sign. Because why? Because I rearranged the equation. What about the second one? It has more fruitful information, which are what? The roots of the characteristic equation, minus 2, minus 1, and minus 2. If we are solving the characteristic equation, we will end up to be what? The roots are what? Minus 1 and minus 2. That's why I'm interested in the first method and the second method. Of course, you can find more than methods, let's say 3 or 4 or 5 or whatever methods in order to find the state space representation. But in the end of the day, if I need to use any representation, it must be useful. The information that I can get from the representation must help me in understanding the system, or later on must help me in controlling the system, because our target in control system is to find what? Is to solve the problem. Yeah, to find the suitable control signal that I should inject to the system in order to what? To achieve certain performance. Yeah. To make the output follows or tracks the reference, yeah, obeying certain requirement or constraint, let's say. Yeah, this is actually the ultimate goal of the control theory. Okay. So, is it clear, Abdullah?
تمام واضح دكتور، شكرا.
Okay. So now, let's see. In the last time, we stated that the general representation for the linear time invariant system, and I hope that you understand the meaning of the linear time invariant system, and why we are interested in linear time invariant system. it can be written as x dot equal a x plus b u, y equal cx plus du. And I think I told you that in general, any physical system, the d for that is equal to 0. D meaning that you have a direct relation between the input and the output with no dynamics. This in general in physics, hard to be found actually. But for generalization, I will generalize it to include all the matrices, which is the A, the state matrix, the B, which is the input matrix, the C, which is the output matrix, and the D, which is the direct input matrix. And simply when I can find D, if the degree of n of s is greater or equal than the degree of d of s, in this case, for sure, you are having what here? The direct input matrix. But in general, the physical system is a proper system, which means that the degree of n of s is less than the degree of the d of s. Now, this is the time domain. In S domain, I think last time we stopped here. Simply, if I need to do this one in S domain, it will be the S, x of S minus x of 0 if I'm respecting the initial condition. Then here I'm having A x of S plus B u of S. And here B is not in step. B is what? Is input. It can be anything, huh? This is, sorry, U. I'm sorry. U is the input, huh? And this does not mean that all the time the input is step. If I'm interested in the step response, in this case, the ultimate input to the control system will be the unit step. But simply here is what? This is the input to the system. For example, if I'm having, let's say, motor, DC motor, let's say, what's the input to the DC motor? What's the input to the DC motor?
Signal voltage.
Yeah, voltage. Huh? Do you see? It's a voltage. Yeah, it's a voltage. Yeah. So this is the input. Huh? This is the input. Something that I can manipulate. Something I can change. Yeah. In favor of what? To getting certain performance, let's say. Now, if I need to find the transfer function, and remember, we are defining the transfer function as the Laplace of the output over Laplace of the input at 0 initial condition, so this will go to 0. Then, if I need to find a solution for x, I need to collect the terms, because here I'm having matrices. I should respect that I cannot add a scalar to matrix unless I multiply by the identity. So this will be S I minus A multiplied by x of S will equal B u of S. Now this is algebraical equation, the beauty of Laplace. So x of S will equal S I minus A inverse multiplied by the B u of S. Now, as we said that the transfer function is the relation between y over r, or the input here. So simply, I need to find the Laplace transform for the output equation. So y of s, this is a piece of cake actually, equal to c x of s plus d u of s. Now, what I can do, plug and play. Do you know the plug and play? It's just how much you can write or how fast you can write, you can get the solution. Yeah, so I will plug it and play here, because I found the solution here, so I will plug it here. So y of s will equal now c si minus a inverse b plus d, all multiplied by the u of s. Now this is my definition of the transfer function, or it's the definition of the transfer function. Huh? So in this case, we will have the output, Laplace of the output over Laplace of the input at 0 initial condition will give me my Laplace or transfer function, let's say, which is the C, the Si minus A inverse B plus D. Good. Now, simply, this is a representation. This one is unique, which means that this one is unique. If I'm having two representations for the same system in the state space representation, if I'm taking the transfer function using C, Si minus A inverse B plus D, I will get the same transfer function. Otherwise, I'm speaking about something else. Now, from here, if I need to calculate the inverse, I must divide by the determinant. So from here, this will come the definition of the characteristic equation in terms of the eigenvalue problem. So the characteristic equation is actually the solution of the eigenvalue problem. So Si minus A equal to 0 as a determinant is my characteristic equation. Good. Yes. So let's take example now here to highlight the thing here. So let's take a example. Let's go another page and let's start with a simple example. Let's assume that we have the same system with two representations. The first one, x dot equal 0, 1 minus A minus B x plus 0 D U, the first representation. And I'm having the second representation, which is Z dot equal to minus 3, 0, 0, minus 1, Z plus 1, 1, U. And here I will write Y also. It's minus 5, 5 multiplied by the Z. And here I'm having Y, which will equal 10, 0 multiplied by the X. So here I'm having system which is represented in the phase conical form or the first method. Also the same system represented in the diagonal form. And if you notice, I change the state variable, yes? Yeah. And this is for sure to respect the math and the physics, because if this one was current, for example, this maybe Z would be what? The current plus the voltage, correct? So I cannot say that X1 is equal to Z1. If this is correct, then this one and this one must be identical. Yeah. Simply here, I'm changing the state variable. And as a result of changing the state variable, the description of the system is differing, although I'm describing the same system. Yes. Yeah. So who can help me to find the transfer function here? The transfer function T of S, which will the output Y of S over the of S. Who can help me to find that? Let's return back to the previous. You see it? Anyone can help me, or I should help myself? Raha Muhanna.
Yes, doctor.
Can you help me to find the transfer function for the first system? This one?
I'll try, okay?
Okay, let's do the math. So the first thing, I will multiply C. Where is C?
10 to 0.
Yeah, thank you. This is the C. So here I will write 10, 0, multiply by what?
S.
Yeah, this is the okay. So here I will write the S. Okay. Okay, you are seeing C, S, I minus A inverse, yeah, B, yes or no? Okay,
Yeah,
so this is the C. Now the second one, where is it? Si minus A inverse. So here the inverse.
I equals A, I guess.
I equal A. Okay, let's evaluate this one. Can you evaluate this one for me? You know that this is S 1 0 0 1 minus the A, which is the 0, 1, minus A, minus B. Can you evaluate this one for me? Can
1 minus 1.
1 minus 1. So this will be 1 minus 1. So let's inject this one here inside this one. So this will be the S. Now, can you help me with that? So the first one is S. The second one? Minus 1. Thank you. The third A. Thank you. And B. Yeah?
Yeah? S.
Yeah, there's S. So S
plus B.
plus. Yeah, thank you. You see? Now you become, let's say, more powerful than me because I forget the S, but you did not. That's good. Thank you. So S minus 1, A, and S plus B, the inverse. Then I will multiply by the B. The B is what here?
0, D.
0 and D. Now, this is a second or 2 by 2 matrix. Can you find the inverse for me?
We find the determinant first.
Yeah. So the determinant is?
S squared plus SB.
Okay.
Minus plus A. Yes.
Okay. Yeah, then I will tuple.
Yeah. Minus 1.
Okay, and minus A1. Yeah.
Yeah.
So I will exchange the diagonal and invert the sign of the off diagonal. Then I will multiply. Of course, I think you are excellent in multiplication of the matrices. If I do the, let's say the math, if I do the math, I will get what? I will get the transfer function. I will get the transfer function, which is the 10d over s square plus bs a. This is the first transfer function. Now, if I return back here and do the same thing, if I do the same thing, which is the c, the y over r, which is the c,
minus 5
and 5, then it is the s plus the 3, 0, 0, s plus 1 inverse, multiplied by the b1 and 1. Now, if I evaluate, I will get it is 10 over s square plus 4s plus 3. Now, Raha, can you tell me the value of the d is equal to what?
D هنا 0.
D.
Hi D. 1.
1. And the value of the b?
4.
4. And the value of the a?
3.
Yes, because two rational functions are identical if and only if n equal to n, and this is n1 d1. Let's say this is n2 d2. So simply n1 must equal to n2 and d1 must equal to d2. And if we do the comparison, then I will get d equal to 1 and b equal to 4 and a equal to 3. Yeah, good.
Yes.
Good. Yes. Okay. Okay. Now let's discuss another example here. Another example. Let's assume I'm giving you a signal flow graph. Let's assume that I'm giving you the following signal flow graph. And this is, let's assume, the U, the 1. Here I'm having the 1 over S. Here I'm having a factor, let's say A. And from here to here, I'm having a feed forward path with certain gain or transfer function. After that, here I'm having 1 over S. And here I'm having certain transfer function B. And this be Y. Now, from here, I'm having a feedback with, let's assume, minus K. And here I'm having another feedback with a minus D. And I need you to find the state space representation giving that I'm telling you that this one is x1 and this one is x2. Can you find the state space representation? Which is the matrices, the A, the B, the C, and the D if exists. And let's choose Haytham Burhan. Haytham Burhan. Haytham, no? Okay. Dana Murad. Dana. Dana, no? Ru'a. Ru'a, no? Uh-huh. Someone is putting on speaker, man, and this will make echo, huh? So simply you are opening the speakers. Okay, whatever. Muhammad Umar. Muhammad Umar Abdul Rahim Sabah. No. Muhammad Iyad. This will make easy for me later on. Muhammad Iyad. No. Talal Islam. Okay. Muhammad Nidal. Tariq Samir. Anyone can help me? Anas Khalid. Should I help myself? Anyone. Jamal Jaradat, for example.
دكتور بدنا نختار اللوبس ونختار الباثs عشان نجيب transfer function x1 و x2.
You are living where? One second.
بعمان.
Okay, so simply if you need to go to the university, you will go to Aqaba, then you return back to university?
No.
Oh, so no. So simply, let's see. If this one is x1, this is what? This is the integration of x1. So this is what?
x1 dot.
Thank
x1.
you.
Yes.
Yeah, x1 dot. And if this one is x2 and I'm integrating, this is what?
x2 dot.
Okay, thank you. Can you write x1 dot equal to what now from the graph? x1 dot equal to what? Equal to what? A multiplied by
x2.
So A multiplied by x2, then
minus alpha x1.
This is alpha. I think it's D, but simply I will follow you. It's alpha. Okay, it's alpha. So minus alpha x1, then
plus f
fu.
Plus fu. So this is the first. State equation. The second state equation, x2 dot equal to what? Where is it? This one. Equal to what?
U of t.
U of t.
Minus kx1.
Minus kx1. Yes or no? Yeah. Y equal to what?
bx1.
bx1. So can you give me now, if I need to write it in matrix form, so x1 dot, x2 dot, or sometime I will write it as d by dt of x1, x2 is equal certain matrix multiplied by the x1, x2 plus certain matrix multiplied by u of t, and y will equal certain matrix multiplied by the x plus d matrix multiplied by the u. Now, can you help me to fill those matrices? Here,
minus alpha.
Minus alpha, thank you. This one.
A.
This one.
F.
F, thank you. Here.
Minus K.
Thank you. Here.
0, 1.
Here. Thank
1.
you. Here.
B. 0, 0.
Yeah. So instead of going to Aqaba in order to go to the university, you are coming via, let's say what, via Hijazi or whatever you call it. Huh? Yeah. Of course, I respect your choice. It's correct. You can find the transfer function. Huh? Then you can respect the, let's say, the selection of x1, because x1 must be selected according to this one. Huh? It must be by. Yeah. So, and x2, so simply that will be very difficult actually. Huh? This one is very simple and cheese of cake. Huh? Good. Yes.
Yes.
Good, good. So now let's see. In general, what I'm interested, this is a model. I need to study the performance or the response or the behavior of the system for specific input. So I need to find the solution. I need to find the solution. Now, if we write the solution, if we write the solution in time domain, let's say, for a general system, which is written as x dot equal ax plus bu and y equal cx plus du. Now the solution here is x of t is equal exponential of at x of 0, the initial condition, plus the integration from 0 to t exponential of a t minus tau b u of tau d tau, which is the dummy variable of the integration. Now, of course, if I need to find the output y of t, it will equal to what? C x of t plus d u of t. So simply I will plug this one here and I will find the output. Now, the most important thing is this matrix or this term. This is called the state transition matrix. And I need to evaluate the exponential of a of t. Sometimes we call it phi of t, which will equal the exponential of a of t. Now, how to find this one? Now, this system has input, yes or no? Yeah? The system has input, yeah?
Yes.
Yes.
So this is called forced system, huh? Forced system. This is forced system because I'm having what input. This is called forced system because I'm having input. Now the unforced system, the unforced system. The meaning of what? U of t equal to what? To 0. I don't have input. If I don't have input, then x of t equal to what? X of t will equal exponential a of t x of 0, yes or no? Yeah?
Yes.
Okay. So now, if there's no input, then the response is caused by what? By the initial. For example, if I'm having the following example, and here I'm having a ball. If I just release the ball will move, yes or no?
Yes.
Yes.
Under what? Under the force, external force, or under the initial position? Due to what?
Position.
So this actually is called unforced system. Why? Because now the behavior here is due to what? The initial condition, huh? The initial condition. Yes. So simply this means that this means that I will have x dot, which will equal ax, yeah? I don't have any input. In Laplace, in S domain, what I will get? I will get S, x of S, plus x of 0 should equal a x of S. Why here I'm keeping x of 0? Because I need to study the response due to what? To the initial position, yeah? Initial condition, let's say. So here, this will be the S I minus a x of S equal x of 0, yes or no? Yeah? Yeah? Yes or no? Oh, good. Now, so if I need to find x of S, this will equal to what?
Inverse.
S I minus a inverse of x of 0, yes? Yes or no? Yeah?
Yes.
Yes.
So simply this means that x of S is equal phi of S, x of 0, yeah? So phi of t will equal to what? Laplace inverse of what? Of phi of S, yes? So phi of t will equal Laplace inverse of Si minus a all inverse, yeah? And this will equal to what? The exponential of at. Good? Yes? So how to find the state transition matrix? How to find this one? Simply by taking Laplace inverse of Si minus a inverse. Of course, there is another method. Someone will say I can use the series expansion. Someone will say no, I can use Cayley-Hamilton theorem. If you heard about Cayley-Hamilton theorem in the linear algebra, which states that each and every square matrix fulfill its own characteristic equation. Simply, this is up to you to look for that. Good. Yes. Right. Okay. So simply, I think this is the end of the chapter 3. If you don't have any question, I will go to chapter 4. No question? No questions?
دكتور ما في examples على هذا آخر إشي كتبناه عن 5S. Yes.
This one? Okay.
Yeah.
I will give a simple example. Let's recall. Do you remember the first example we started with? I forget it actually.
1 over S
Equal
squared.
to, the first one was what? Here 0, 1. I think here is minus 2, here minus 3.
Yes.
Yeah, x plus, I think here is 0 and 1. And here I'm having the R or the whatever input I'm having. And Y, I think here it was x1, correct? Yeah. And the second one, the same representation, x dot was equal to, I think here it was minus 1, 0, 0, minus 2. Yeah, I write minus 2, thank you. X plus 1, 1. R and Y, I think it was some 1 and minus 1, huh? 1 or minus 1, 1?
No, 1 minus 1.
Thank you. Okay. Now, who can calculate here exponential of AT equal to what? Exponential of AT equal to what? Now, this will equal Laplace inverse of SI minus A inverse. So the first thing, let's find SI minus A inverse. So this will be the S minus 1, the 2, the S plus 3. Yeah, the inverse. Yes. Now, if we do the math, this will equal to what? 1 over the determinant, which I think 1 over S plus 3. Yeah. S plus 3 plus 2. Yeah. Then what I will do plus 3. And do the math will be, this will be something like this one. This will be s plus 3 over s square plus 3s plus 2. Yeah, first one. Here I'm having 1 over s square plus 3s plus 2. Here I'm having minus 2 over the determinant, because I will not write this one again. And this will be s over the determinant, correct? Yeah?
Yes.
Can you find Laplace inverse for this one? Yes or no? Yeah, of course you can. This, you are evaluating Laplace inverse for 4 terms. The first one, the second one, the third one, and the fourth one. And because I'm too old, I will take this one as an example. So I need to find let's say Laplace inverse for which element? Let's say 1, 2. The first column, the first row, sorry, the first row, the second column. So if I need to do Laplace inverse, this is, yeah, I'm lucky. This is my lucky day. So it's 1 over s plus 1, yeah, or k1, let's say here, plus k2 over s plus 2. So automatically, if I need to take Laplace inverse, this would be k1 exponential minus t plus k2 exponential minus 2t. Yeah? Yes?
Yes.
Yeah.
Yes.
And you will do it here and here and here and there. Yep.
Yes.
Good. Any question?
No.
Okay. So let's go to start chapter 4. Which is simply the feedback control system characteristic. Now, you know, in general, we have this one, open loop, in which if this one is R of S, and here I'm having D of S, and this is the plant, which is the G of S, and this is the output is Y of S. Now here, the input, or the command signal U of S, is the function of what? Of the desired output. This is an open loop configuration. Or simply if we have a general, let's say, block diagram. Here, let's say controller I'm having GC of S. Here I'm having disturbance, let's say D of S. Here I'm having the plant. Let's assume this is the G of S. Here I'm having the output Y of S. And remember, you need to measure the output, yes or no? I need to measure the output. So for sure, I will have certain noise, N of S. Why? Because any sensor has a noise, yeah? Then here I'm having what? I'm having feedback, which is the H of S due to the sensor, due to the controlling. Then this would be the negative feedback minus, and this would be the R of S. Now, this is actually called the open loop configuration. And this actually is called what? The closed loop configuration. Now, let's agree that we are define the tracking error. As E of S equal R of S minus Y of S. And this actually is what the objective, this is actually what the objective of any control system, correct? The objective of any control system is to minimize this equation, yes or no?
Yes.
In the end of the day, I need my controller to force the system, let's say, such that the output obey or follow, or let's say tracks the command signal, correct? So Whether I'm discussing open loop or closed loop, it will be the same. Yes or no? Yeah, it will be the same. Okay. So now, who can find the error signal here? E of s here equal to what? For this one. Or let's say y of s, y over r equal to what here?
G of S, D of S plus R of S.
Just a minute. This is y over r, so it will be g of s.
G.
Yeah. So now, if I'm telling you find y of s equal to what? You will telling me it equal to what? It will equal g multiplied by r plus d. Yeah. So can you find the error signal now equal to what?
ما في feedback.
So E equal to what? So E will equal to
of
1
S.
minus y over r multiplied by what? By r. Or simply, if you need to make it more interesting and easy, you say that I'm having the y, so I will substitute it here, yeah? So E will equal to what? Will equal to r minus gr minus gd. Yes? Yeah. And this is E will equal to what now here? This will equal to this will equal to 1 minus G multiplied by the R plus or minus 0 or minus G multiplied by the D. Yeah. Okay. Yeah. So even though I don't have a feedback, still I can calculate what? The error signal. Why? Because even if I cannot see it explicitly, implicitly I'm having error signal. Yes, because the objective of any control system is to minimize the error signal. Even if you cannot see it, even if you cannot see the error signal, it's still there. Yes. Yep. Now what about this one here? Who can find the error signal, which is E equal R minus Y? Y equal to what here? Y equal to what here? Will equal certain transfer function T1 multiplied by R of S plus another transfer function T2 multiplied by D of S plus third transfer function, yeah, 3 of S multiplied by N of S. Why? Because here I'm having 3 inputs. The first one is the actual input. The second one is the disturbance. The third one is the noise. The third one is what? Is the noise. Now, if I need to find it, if I do the Mason-Gunn formula, and simply, I think now you are experienced in doing that, this will be GC, G over 1 plus GC, G multiplied by the R plus G over 1 plus GC, G multiplied by the D minus GCG over 1 plus GCG multiplied by the N. Yeah. Yes.
دكتور مش المفروض عندنا feedback H؟
Yes, so because I'm too old, let's assume that for simplicity, let's assume that H of S is equal to 1, yeah, which actually what we call the unity feedback. You know that simply I can solve it with no issue, huh? See the beauty of the loop shaping. You see this one? Huh?
Yeah.
If I need to remove this one from here and put it here, what I should do? I need to put this one here. So if I'm putting this one here, I must divide this one by h, yes or no?
Yes.
So simply I'm getting the same, huh? So see the beauty of this thing, huh? Allow me to do that. Now here, I will say I will have h, gc, and I will call this one gc prime, something called controller, yeah? Do you care about? No. And here, I will say that I'm having here 1 over h, and this will be the r of s, and I will say that this is r of s dash. So I will get the same, huh? Instead of r, I will put r dash, and instead of the gc, I will put what? gc dash. Yeah? So without loss of generality, I can assume what? I can assume that h of s is equal to what? To 1. And this is the beauty of something we call loop shaping. Huh? I'm shaping the loop. Good. So now, let's see. In the end of the day, I need to calculate the error. So E is defined as what? R minus Y. So if I calculate this one, this will equal 1 over 1 plus GCG multiplied by the R minus G 1 plus GCG multiplied by the D plus GCG over 1 plus GCG multiplied by the N. Yeah? Simply how to do that? Plug here Y and evaluate. So this is the E. Yes? Yeah? Okay. So now let's see. Let's define this one as S of S, which equal 1 over 1 plus GC of G, and this indication of the sensitivity function. Yeah. Good. And let's assume that I'm having S of S plus C of S equal to 1. And C of S is the complementary sensitivity function. So simply here, if I do the math calculate here, C of S will equal to GCG over 1 plus GCG. And this is the what we call complementary sensitivity function. Complementary sensitivity function. By definition, now why I'm interested in defining sensitivity function and the complementary sensitivity function, because the error now, the error signal, this one here, I can rewrite as, in terms of the sensitivity and the complementary sensitivity, as E of S equal S of S R, yeah, minus G S of S D plus C of S N. Yes or no? Yes or no?
Yes.
Good.
Yes.
Now, if I need to minimize the error due to the input and the disturbance, what I should do? If I need to minimize the error caused by the input and the disturbance. What I should do? Make this factor equal to what?
To 0, صح?
To 0, yeah. You know there's another solution. Make R equal to 0 and D equal to 0. Do you know this solution is called what?
No.
Trivial solution. So simply, if you need to make your electricity bill 0, don't use the electricity, man. But you should pay. You will pay 6 JD, yeah, by the way, even if you don't use the electricity. Yeah? And this is the beauty of the mathematics. Okay. So simply, the only thing I need to minimize this one. Huh? Now, if I need to minimize the effect of the noise on the error, what I should do?
CS equal to 0 or N equal to 0.
Yeah, but N equals 0, this is trivial, huh? Which means that you cannot use it. By the way, when I'm telling you that R equals 0, D equals 0, N equals 0, I call it a trivial solution, which means that 0 equals 0. There's no problem, there's no solution. This one is what you call it? Nothing. Trivial, nothing, huh? Yeah? So the only thing I can do is what? Is to make this term or minimize this term, huh? To minimize this term. So we are getting in serious problem, man. Do you know what's the problem? The relation between the S and the C is governed by the following equation, yes or no, or following relation, which means that S plus C equal to 1. So if I need to minimize this one, for sure I will maximize this one, yes or no?
Yes.
And if I need to minimize this one, I will end up to what? To maximize this one, yes?
Yes.
So we are ending up with a problem. I can't satisfy it 100%. Can I?
No. ما بتقدر إنه 100%.
So what I should do? I should do trade-off. Do you know the trade-off is what?
تشوف أي أفضل.
To find a compromise solution that can achieve the two things. Yeah?
Yes.
But how I can do that? How I can do that? How I can do that? Who can help me with that?
Make them equal.
ها؟ ايش هو؟
خليهم يساووا بعض نص.
No. This is actually you are what? You are closing your eyes. You are closing your eyes and say that I don't care. No. Now let's see. Do you know something called frequency response?
Yes.
And you know that this is omega, and this can be seen as amplitude, yeah? Amplitude. Okay. Now let's see. So here I will write the amplitude of the S and the amplitude of the C. Now let's assume here I'm putting certain threshold for frequency. Let's assume this is F0, and say that below this frequency, this is low frequency. And above this frequency, high frequency. And simply, who will decide this one? Your application, yeah? Your application. So sometime I can consider 1 hertz as low frequency. Sometime I can consider 50 hertz as low frequency, correct? Because it depends on the order of the magnitude, yeah? On the order of what? Of the magnitude, yes? Until here, is it okay? Okay. Now, let's see how many inputs I'm having. I'm having the disturbance, and I'm having the noise, and I'm having my input. Yeah?
Yeah.
Correct. Okay. Now, the disturbance is characterized in the low frequency region or the high frequency region. The first thing, do you know the meaning of the disturbance? It's unwanted input, yeah?
Yes.
And if I'm telling you, can you give me example for disturbance? You will say it's a wind speed, yeah? Right. The wind speed or the wind direction is what? Is a disturbance, yes or no?
Yes.
Now, can the wind direction and the speed change in high frequency rhythm or pattern or in low frequency pattern? or
low.
in low. So simply this means that disturbance is characterized here. And the noise, by the definition of the noise, it's what? It's high frequency.
High frequency.
Do you know the white noise, for example? Yeah, it's what? It's high frequency signal. So someone will say, can I design the loop gain? Can I design the loop gain, this one, such that it has a high amplitude at low frequency, and low amplitude at high frequency? So if I'm plotting here, let's assume the amplitude of GCG. Can I design it such that it will have high amplitude here and very low amplitude here? Yes or no?
هسه الأمبر مش هو بزبط على الفلتر.
شو بزبط على الفلتر يا ابني؟
الباندويث يعني بتقدر تاخذ اللي هو تحدد الفريكونسي اللي انت بدك اياه.
And the controller is what actually?
مش عارف.
The controller is what? Transfer function, huh? Or in relation, yeah? Relation. Yes. So simply you can control the frequency response of this relation, yes or no? Because you are designing the controller, yes? Yeah?
Yes.
Yes?
هيك المفروض.
هيك المفروض. Yes. So simply this means that I can design my controller such that the loop gain, let's say GCG, has high frequency, high amplitude in the low frequency. In this case, S will be reduced. Yeah? Yes or no?
Yes.
And C will be increased, but I don't care about this one. Why? Because there is no noise. Yeah? The noise is not characterized here.
Right.
Yeah?
Yes.
Then the same, let's say, loop gain has a low amplitude here. So here, high amplitude. And here I'm having the low amplitude. In this case, C will be reduced. S will be increased, but I don't care about S. Why? Because there's no disturbance there. Yes or no?
Yes.
And this is how I can solve what we call disturbance, let's say rejection, or not rejection, it will be disturbance, okay, disturbance rejection and noise attenuation. This is how I can achieve what we call it disturbance rejection and noise attenuation. So canceling the effect of the disturbance is called disturbance rejection. And canceling the effect of the noise is called noise attenuation. Yeah, because they are characterized in different, let's say, frequency range. So now, what is, let's say, has the ability to reject the disturbance, the open loop or the closed loop? If I recall the open loop, where is it? Where is it? Where is it? Yeah? This is the open loop. Whatever you are doing, you cannot reject the disturbance. The disturbance already appear here. Huh? Yes?
Yes. Yes.
So whatever you are doing, you cannot reject or suppress, let's say, or eliminate or reduce the effect of the disturbance. But in the closed loop, simply using a feedback, I can not only reject the disturbance, but also I can attenuate the noise. Yes?
Yes.
Good. Now, sometime you will hear about the sensitivity of certain transfer function with certain alpha. Example. Let's assume that I'm having RL circuit. Recall. Here I'm having RL circuit, and let's plot it here. And this is the R, this is the L, and this is the V. Let's assume that I'm interested in the current here, I. So I over V will equal to what? I think last time we discussed 1 over LS plus R, yeah? Yes? Yes or no? So if I need to plot this one here, the input is the voltage, and here I'm having the relation of the plant, which is 1 over LS plus R, and here I'm having what? The output I. Yeah? Now, this is an open loop, yeah? This is an open loop system. So simply if I need to make the current, let's say, equal the input, I can do very simple controlling here. Yeah, I can say that. I will make this one I reference or I star. Then here I will multiply this one by R. And now here, this is what? The voltage. Yeah? Can anyone give me the closed loop transfer function now? Now the input is what? The reference current. And the output is what? The actual current. Yeah? Yes?
Yes.
Now, can you give me I over I star equal to what? It will equal R over LS plus R. Yes? Can you give me E steady state equal to what here? Of course, if I need to specify the error, I must specify the input, huh? Due to unit step. So E steady state equal to what?
Limit when S goes to 0.
Okay, let's do the math. Okay, the limit when S go to 0 of S, E of S. So, come on.
0.
0, thank you. Why? The DC
Well,
gain here equal to 1. Yes?
Yes.
The DC gain here equal to 1. And that's why here I'm multiplied by R, by the way, in order to make the DC gain equal to 1. And if the DC gain equal to 1, this means that the output will equal to the input in the end of the day if the system is stable. And this system for sure is stable because L and R are a positive number because they are physical quantity, yes or no? Can you see negative inductance? Can you see negative resistance? Yeah?
No.
So simply this to yes. Yeah?
Yes.
Okay. Now see. This one is a physical quantity, yes or no?
Yes.
This one is what? This one is what?
The same physical quantity.
لا يا راجل. لا يا راجل. So you need to make the current inside the circuit equal to certain value. You will bring another resistance until the system, or let's say hit the system by the resistance and say that, hey, this is the resistance. Inject the voltage. This is a number, man. Number. Gain, let's say gain. Yeah? Gain. Okay. Yes or no? It's a gain.
Okay.
So this is a value. Number. This is a physical, yes, this is a value. Yeah? Yes or no? Good.
Yes.
Now, see. Do you hear about something called mismatch between the actual value and the nominal value?
Yes.
So simply you are calculating this one and say that R equal to 10 ohm. Yeah? Or from the color of the resistance or from the measurement, you are saying R equal to 10 ohm. Then you are going to the simulation or whatever, to the computer, and say that R equal to what? To 10. Yes, R equal to 10. But unfortunately, this is not 10 ohm. This can be plus or minus certain tolerance. Yes.
Yes.
Certain delta R. Let's say. Now here, this is called what? Mismatch. Yes. Another thing. Now you are measuring this resistance. Come to this resistance after 1 year. Measure it again. It will be the same value. Maybe, maybe not. This we call it what? Aging effect. Do you know the meaning of the aging effect? Of course, you should know what the meaning of the aging effect. Yeah, because you are observing that all the time. Yes?
Yes.
Yeah. If you return in the back in the memory before, let's say 5 years, you can see yourself something else. Yeah.
For sure.
Yeah. So the aging effect, which means that this value is designed based on the best knowledge. Yeah. In our best knowledge say that R equal to 10, but unfortunately it can be what? 10 plus minus something, certain tolerance. Someone say, wait. I will measure it. I will tell you, okay, measure it. If you measure it simply, and if I'm telling you register your value, someone will say it is 9.51. Your friend will say, wait, why you are right? It's 9.5, man. I don't care about the one. So this is what we call reading error or measurement error. Yeah. Someone will say, I will go to the same factory and take the same elements. I will tell you even. If you are taking the same resistance from the same, let's say, line in the factory, you cannot get two identical elements 100%. It's impossible. It's what? Impossible. There will be a mismatch. So now what I need to study, what will happen to the transfer function if certain parameter change, let's say R change. And this simply I can define it as the percent change in the R to the percent change in the G, let's say. Yeah? So this simply I can define it as the ratio of the percent change R, or percent change on G, sorry, to the percent change on R. To the percent change on R. So simply this means that it is G over delta G. I'm sorry. So it's delta G over delta R over R, which I can rewrite again as delta R. Okay. Now this one can
delta G multiplies by
yeah, delta G over delta R multiplied by
R over G.
R over G. Yeah. Yes.
Yes.
And what I need to make this value as absolute value, of course, because there's no meaning for the plus and the minus. I need to minimize this one. If this one is very, very small, then the system is less sensitive to parameter variation. Okay. If this one is very small. So, and let's assume that I will give here a small example. And the same problem, I will use only a feedback. Who can find here the closed loop transfer function? T equal to what? T open loop, let's say, open loop. The closed loop transfer function for the open loop equal to what? And T for the closed loop equal to what?
G.
G. And here?
1/1 G.
G over 1 plus G. Thank you.
Okay.
Now, let's assume that I need to study what will happen. What will happen to the closed loop if the open loop is changing? Yeah. So the first one here, who can evaluate this one? Still, I'm have it here.
نفس المعادلة هاي. أيوة نفس المعادلة.
Yeah. So can you put this one here? So this will be what?
Delta G
T over delta G over T. Yeah.
Yeah.
And this will equal to what? Because G equal to T, this is equal to what?
G equal to G. Delta T over T.
And delta T is delta G, man.
Okay.
Yeah?
Okay. Yes.
So this equals to 1.
دكتور هلا إذا جي وتي نفس بعض مو ضروري دلتا تي ودلتا جي زي بعض صح؟
G and T are the same, yes or no?
Yeah, but the difference ممكن يكون غير ال percent change.
Okay, just a minute. Y over R is equal to what? G. Yes?
Yes.
And this one is equal to T, yes or no?
Yes.
So delta G is equal to delta T here in this example, yes or no?
Okay.
So similarly, this means that the open loop is highly sensitive to what? To any change in the plant, yes or no? Any change in the plant, you can see it, yeah? Now, before finishing, this one, who can help me with that? Who can help me with this one? T close as delta T over delta G, then G over T. If you do the math, this will equal to what? This will equal 1 over 1 plus G. Yeah. Now, as absolute value and absolute value, this one is less than 1. Yes or no?
Yes.
So simply this means that the sensitivity of the open loop is higher than the sensitivity of the closed loop.
Yes.
So simply using only a feedback make the system less sensitive to what? To the parameter variation. Yes?
Yes.
And not only that, I can make 1 plus G, for example, very, very high. So simply this means that C of T closed loop over G is almost 0, which means that anything happened to the plant, I cannot see it. I cannot see it. Yeah?
Yes.
Do you have any question before finishing this lecture?
لا دكتور.
Okay. So keep distance, stay safe, ويعطيكم العافية.
الله يعافيك دكتور.
السلام عليكم.
عليكم السلام.
دكتور لو سمحت.
تفضل.
دكتور بقدر احكي معك بموضوع برا المساق انه بخصوص او شيء كونه رئيس قسم.
بتقدر يعني ما فيش مشكلة.
دكتور هسه في يعني لا بالالكترو
خليني بس اعمل turn off just a minute. It has no relation. صح؟ Just a minute. So stop.